tell you about my best friend. He's a warm-hearted person who loved me till the end. People, let me tell you about my best friend. He's a one-boy cuddly toy, my up, my down, my pride and joy. People, let me tell you about him. He's so much fun. Whether we're talking man to man or whether we're talking son to son, 'cause he's my best friend. Yeah, he's my best friend. La la, ba da 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 ya, ba da 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 ba da 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 ya, ba da beep beep, bo bo.
How many of you back in the days when you were childish used to play with little rubber band slingshots like this? Huh? You're not scared? Cool. Well, things that can be stretched or coils that can be compressed, bro, have what's known as elastic potential energy. Anything that can be stretched, anything that can be stretched or compressed has elastic potential energy. Right now, looking at this rubber band, I don't think that it has the ability to do any work on anything. However, if I stretch it, it now has the ability to do work on something if it were to be hit. If I stretch it even more, it has a higher ability to do work on something. Same goes with coils or springs. The more you stretch it, the more ability it has to do work on something. Or coils that can be compressed have potential to do work on other things. I'm going to teach you a little bit more about that, and we're going to talk about calculating elastic potential energy. We also know that all springs are not created equal. Same with rubber bands. If I had a pack of assorted rubber bands, you'd know that there are some that are thicker than others, there are some that are thinner than others, and we would call that a spring constant. It's essentially a way that we measure the stiffness or looseness of a spring, because that would affect its ability to do work on something. But I only have these two because coronavirus, so yeah, let's talk a little bit more about that now. Elastic potential energy is energy that's associated with the position of stretched or compressed objects. That could be anything like a spring or even a rubber band slingshot that you used to make in elementary school. Let's learn about the formula for elastic potential energy. Elastic potential energy is equal to half of K times X squared. EPE stands for elastic potential energy, and K stands for the spring constant, which is measured in newtons per meter. The spring constant is simply how stiff or how rigid or loose the spring or rubber band or whatever object is. X is represented by the distance stretched or compressed. If you're going to have elastic potential energy, that spring or that rubber band has to be stretched or compressed. Practice problem number 1. If Tamir stretches a rubber band back 4 meters and the band has a spring constant of 4 newtons per meter, how much elastic potential energy does this band have? The first thing that we would do in class is pull out our givens. Reading this problem, the first number I see is the rubber band is stretched back 4 meters. Is that EPE, spring constant, or the distance stretched or compressed? I'd say that that would certainly be the distance that it was stretched. So that is 4. Next, the band has a spring constant of 4 newtons per meter. That's quite obvious that that has to be K, which means our spring constant is equal to 4 as well. The question is asking us, how much EPE does the band have? Well, obviously we are solving for elastic potential energy. So we use our formula. EPE is equal to half of K times X squared. We plug our values in. EPE is equal to half of 4, which is the spring constant. I'll put that in parentheses here, times the distance stretched, which is also 4. But please see that that 4 needs to be squared. Cool, let's do some basic math. EPE is now equal to half of 4. And since I was in first grade, I knew that half of 4 is equal to 2. And 4 squared, 4 times itself, is equal to 16. Therefore, the elastic potential energy of this rubber band must be equal to 16 times 2, which is 32. Elastic potential energy is energy, so the unit is joules, because you always put the unit, like you always put the unit.
you always put the unit. Like, you always put the unit. And a little box around that answer as well. Awesome. Practice problem number 2 is on the way. So, here we are. If this rubber band is stretched back 2 meters, which it's obviously not, and has 200 joules of elastic potential energy, what is the spring constant of these bands? How rigid or how stiff or loose are these rubber bands? So, we're using our formula again. The first number I see is that the band is stretched backwards 2 meters. Therefore, X is equal to 2. And it tells us that it has 200 joules of elastic potential energy. Therefore, EPE this time was given as 200. The question is asking us, what is the spring constant? So we are now solving for K, the spring constant. We'll use our formula. EPE was given to us this time. That means 200 is equal to half of K. We don't have K, we're solving for K, so we just put that in there. Times X squared, and X is 2, so times 2 squared. We do our basic math here. 200 is equal to half of K times 2 squared. I'm just going to rewrite that. And we know that 2 squared is 4. Come on down, write it again. 200 is equal to half of K times 4. Half of 4 is 2, and then we'll multiply that by K. Then we'll divide by 2 since it's being multiplied by 2 when we want K by itself. Those 2's cancel, and therefore 200 divided by 2 is equal to 100. So K is equal to 100. The unit for the spring constant is newtons per meter. That's how much force it will take to move that spring a distance. The spring constant is 100 newtons per meter, and you always put the unit. Awesome. Let's go ahead and do our last practice problem. Practice problem 3. If the spring that's shown in this video above has a spring constant of 6 newtons per meter and has a total elastic potential energy of 48 joules, how far has it been compressed? Same handy dandy formula. We pull out our givens. It says that the spring has a spring constant of 6 newtons per meter. So therefore, that it must be, you guessed it, they have given us K. K is 6. And it has a total EPE of 48. So our elastic potential energy this time is 48. How far has it been compressed? That must mean we are looking for X this time, the distance that it was stretched or compressed. This spring was being compressed, not stretched. We plug it in. EPE is equal to 48. So therefore 48 is equal to half of K, which happens to be 6, times X squared, and we're solving for X. Do our basic math. 48 is equal to half of 6. Half of 6, I note, is 3 times X squared. We now need to get X squared by itself. It's being multiplied by 3, so we should divide by 3 on both sides. Those 3's cancel out. 3 divided by 3 is 1. So therefore, X squared is equal to 48 divided by 3. 48 divided by 3 is equal to 16. But please remember, we're solving for X, not X squared. So what times itself equals 16? If you don't know off the top of your head, you can simply do the square root of 16. And when you put that in your calculator, you will find that the square root of 16 is equal to 4. That means that that spring was compressed a distance of 4 meters, and you always put the unit. The unit for distance has always been meters since August. All right, those were our 3 practice problems, and I didn't have to tell anybody to be quiet. Look at that. Good job. Well, did you enjoy that lesson? Huh? All right. But go sit over there then. Go sit over there then. Oh. Whatever.
People, let me tell you about my best friend. He's a warm-hearted person who loved me till the end. People, let me tell you about my best friend. He's a one-boy, cuddly toy, my up, my down, my pride and joy. People,
Oh, calm down. What?
I'm trying to record a video. Jeez. Okay. Hey.